All right, so here is Maclaurin series expansion part 2, where I promised I would show you some stuff. If you'll notice, I have another window open here, and that's so that I can write some stuff to you so you can see it as well. So the two expansions that we saw so far were sine of x is equal to x minus 1 over 3 factorial x to the third plus 1 over 5 factorial x to the fifth minus 1 over 7 7 factorial x to the seventh plus dot dot dot, and cosine of x 1 minus 1 over 2 factorial x squared, which is just 1/2, but still plus 1 over 4 factorial x to the fourth minus 1 over 6 factorial x to the sixth plus dot dot dot. Those are the ones that we saw so far. And what I wanted to show you was a little bit more about that. We'll come back to this screen a little bit later when we want to look at some notes. So far here, I have the sine function. This is a great graphing program called Desmos. If you've not played with it, it's really flexible and it's pretty awesome. If you don't have a graphing calculator, Desmos can do pretty much most of the things that the graphing calculator can do in neat little ways. Anyway, so let's go over here to the input screen for Desmos, where I put in sine of x. And so what you'll notice here are the various terms of the Maclaurin series expansion of sine of x. I have just the first term, just the first two terms, just the first three, just the first four, just the first five. So what I want to show you here is what I'm talking about when I say that the Maclaurin series expansion can be used as an approximation. So what I'm going to do here is I'm going to show you the sine of x graph and then show you each of these graphs laid over the sine of x graph. So sine of x and just x, right? So you'll notice here, not a great approximation, except if we're in this local area. We'll just look at that and we'll come back to it. When I add a term, look what happens there. I end up following more of that curve, but then, the approximation fades away as being good around like -1 and +1. It kind of falls away. And so here, when I use the first three terms, you can see that until about x equals 2, it's a pretty good approximation, but between 2 and -2. And of course, these are radians, by the way. So there you go. Kind of makes sense there. There's your 3.14 or pi, right? And then if I use the first four terms of the expression, look, I have a good approximation out to about 3. Use the first 5 terms, a good approximation out to about, I don't know, I'd say here is about 3.75. And I could keep going and going and going. And the more and more terms I use, the better the approximation it is. So there you go. But what we're interested in, honestly, is this idea that I can take my sine of x function, right? Let's just go back to this. And the reason why we like the Maclaurin series expansion is a lot of calculus operations are really annoying to do for transcendental functions. But when you have a polynomial, we know taking the derivative of that is pretty simple. We know there's going to be other things, taking the limits of that pretty simple. And then something we're going to talk about soon, taking the antiderivative of polynomials, super simple. Not so simple for the transcendentals. And that's going to be why we want to be able to transform this into simpler forms. But wait, it gets better. Because if I know, for example, that I only care what's happening near the origin, or like for small values of x. For small values of x, let's look at just x, and let's zoom in here. Notice that between about 0.4 radians and -0.4 radians, that's pretty much identical. There's not that much distinction between the sine function and the x function, y equals x function, in that segment of the domain. And that's really cool, because what that means is if I'm willing to only look at small values of x, then sine of x could be approximated as just x. And so if I come over here and I have then, if I take the limit as x approaches 0 of sine of x, I just actually get x. Now, if you can imagine, that could be really helpful if I have a sine of x and a real complicated function, where if I just take a limit analysis and restrict the function to only looking near value of 0, I can replace all my sine of x's with x's. Now notice here, that's the first term of the approximation. Let's say I can't quite restrict it to real small values. Then I can say, well, okay, not for real small values, but for small values, I can restrict to just the first 2 terms. Or the further out from 0 I have to go, the more terms, like here, if you notice, the first 3 terms here in this zoomed in version, that's almost a perfect approximation. And so depending on how the domain of values I care about and how precise I need to be about the values, I can use just the first couple of terms of the Maclaurin series expansion as a replacement for the complicated function. So what does that mean? Well, these are called the small angle approximations. If I take the limit as x approaches 0 of cosine of x, well, what does that become? Well, if you look at that, that's just the first term of the Maclaurin series expansion, right? So these are what are called the small angle approximations. And we use small angle approximations all the time in physics. In fact, last year, you should have learned 2 times when you use a small angle approximation. Hopefully those 2 times were in the Young's double slit experiment and in talking about the period of the simple pendulum. We'll do the latter of those 2 this year, not the former. By the way, since we're talking about it, we could also talk about the small angle approximation of tangent of x. Well, tangent of x is just sine over cosine, so that's going to equal x, because x over 1 in the small angle approximation. So here's what our small angle approximations are. The sine of x is approximately equal to the tangent of x is approximately equal to x, and the cosine of x is approximately equal to 1, as long as we're willing to restrict the angle to small values. So what's small values? Well, it kind of depends on what your threshold is. If you notice there, it was a pretty good analysis up to about 0.4 radians. So if we plug that into our calculator and figure out what 0.4 radians is, so 0.4 radians times 180 degrees divided by pi, and you get about 22 degrees. So anything in like the 25 degrees or less area, so less than 25 degrees, oh no, less than 25 degrees, if your angle is less than 25 degrees or x is less than 25 degrees, then you have the ability to do that. And that's actually why we do Maclaurin series expansion, folks. We do it to take what we have, turn it into a polynomial, and then talk about approximations where we only need a few terms of the approximation in order to kind of see what's happening with that value in specific ranges. Let's say we don't care about what's happening around 0, but we care about what's happening around, 2. As I talked about before, there's something called the Taylor series expansions that lets me recenter the analysis around a specific value so that we can test around that value and to get the approximations of the curve around that value. It's not just the same thing as evaluating the coefficient f prime at a, where a is the value. There's another thing that has to change in the structure of the power series that you're talking about. It's not that hard of a shift, but it is a shift, and it's not something that we're going to talk about this year. So there we go, Maclaurin series expansion. 2 things you got to know: here's your function, here's how I do it, and the idea that taking just the first couple of terms, if you're willing to restrict your value to small values of x, you're able to do an approximation and get a much simpler function to work with. Okay, so let's end that.